Welcome to a lesson with Dr. Powell. Let's take a look at a function such as x plus 1. And let's do x plus 1 squared all over x plus 1. And let's let this be a function right here. Now, this function, if I were to draw it, well, first, let's find an algebraic equivalence. I can cancel, and I could have just x plus 1, because that would cancel with that. This is an algebraic equivalence, not a functional equivalence, because the domain on this side is different than the domain on this side. When you cancel, you actually get a different function, but it is still algebraically equal. Okay, so using that idea, we can actually graph this function. It looks like x plus 1. Which is shifted that way like that, and looks something like this, except there's something important. This function right here on this side is actually not, you cannot have x equaling -1, because that would make division by 0, and we don't want that. So this right here is actually, it's only equal to this when x is not equal to -1. At least as a function, okay? But if you want to keep this equality being a function inequality, you're going to have to put a comma here and have an x not equal to -1. So now, what if I were to think of the idea of a limit? And I'll notate it this way, right? Lim x approaches, as x approaches -1, as x gets close to -1, is there a y value that I could assign to fill in that hole that would make the function continuous? Well, there is. And that value is, so yeah, I'm taking the limit of this expression. And that value is precisely just taking the algebraic equivalence and plugging in -1. So -1 plus 1. Which is equal to 0. So we can find the y value that we're getting close to simply by canceling things out and changing things algebraically until we get something where we can plug in. That is the idea of taking a limit. So we can think about the y value of holes very nicely with limits. Thanks for watching.